I'm going to tell you a quick story which I'm rather happy about, and I'll try to explain why I'm happy about it as we go along. So I'll begin with this obviously synthetic picture here, where a girl is looking from a beautiful tropical paradise out to an icy waste. And it's obvious that she's not going to go to the icy waste, but how does she know that this is warm and that's cold? And we don't really know the answer to that question, so it is quite a fundamental question. Now, I just, oops, why doesn't that want to move ahead? Sorry, I'm using the wrong one, that's why. I've got it. Now, I just want to roll back the clock to 1996, when I worked with a brilliant Italian student, Paolo Cesare. And what we did was do the first recordings of warm responses from nociceptive, in other words, pain-sensitive neurons. And you can see one here. We applied a 49-degree C flow of Ringer's solution. Now, if you put your hand on the 49-degree C, this will feel slightly, mildly, painfully warm, not very painful. And we got this lovely burst of action potentials. And we found that the stimulus evoked an inward current. That's a heat-sensitive neuron, that's a heat-insensitive one. And we found that the threshold was a bit above 40 degrees, which all correspond with the transition in the English language from warm to hot. So almost every language has got this verbal transition in it, and it reflects this transition here, the activation of these heat receptors. Well, at the time we wanted to clone this receptor and find out what its molecular basis was, but not being molecular biologists, we didn't really see the way forward to do it. And the group of David Julius did this quite by accident, actually. They were looking for the receptor for capsaicin, which they cloned, and of course it's TRPV1. And TRPV1 is certainly activated by capsaicin. And then they had the idea, I think actually from having seen our work, which was published about a year before theirs, of trying heat. And they found that this also activated the receptor, as of course do protons. So it's a multimodal receptor, but its primary function is to detect painful heat, so finger in the candle flame sort of heat. Well, soon afterwards, as you know, and I'm going over ground which is familiar to everybody here, a whole host of these receptors were produced, and many authors produced these kind of optimistic diagrams, and I'm guilty of this as well, showing TRPV2, which is the high temperature receptor, TRPM3, which is sort of mid-range, TRPV1, of course, that we spoke about, the chilly receptor, which is down here in the mid to low 40s. Then there's another couple of lovely ones, TRPV3, TRPV4, that cover the sort of warm temperature range, TRPM8, which is a cold temperature receptor, and finally TRPA1, which appears to be possibly, although it's disputed, a sensor for noxious cold. So we see here a sort of paradigm of going about this. You clone your TRP channel, you express it in hex cells, you observe the response to heat, and you theorize about what role it may play in the intact organism. The question is, does it? Are these the real physiological thermosensors? Well, I have to say this is a bit of a wasteland because they've all been knocked out in various lines of mice, and basically none of them work. TRPV1 knockout has very little effect on the sensation of acute temperature, although it has a profound effect on the sensation of inflammatory temperature, which obviously makes it pharmacologically very important. TRPM3, same story, little, some small effect. I've kind of grayed these out a bit. They have some small effect, but there is no abolition of the sensation of painful heat. TRPV2, no effect whatsoever. TRPV3, TRPV4, wonderful experiments done by Mike Caterina's group. He knocked them out individually, then he did them both together. Absolutely no effect on warmth sensation whatsoever. And finally, TRPA1, again, the knockout of that has very little effect on the sensation of cold. The only man standing is TRPM8. Very nice group work from David Julius's group has shown that TRPM8 knockout has a profound effect on the sensation of cold in this sort of temperature range here. I think the sensation of coolness rather than cold, non-noxious cold. So we wanted really to go back to what we'd failed to do 20 years ago, which is to start with the neurons and ask can we clone the channel? So I think my failure to do that 20 years ago had sort of stuck with me as a kind of a needle in my brain and something that I needed to attend to. So we started with this experiment. So this is just calcium imaging. These are sensory neurons. You can see there are many different sizes, big and small, etc. And these are at rest. And if you activate TRPV1 with capsaicin, you can see that a number of them respond. It's well known that the TRPV1 expressing neurons are small neurons, so that's hardly a surprise. This was known already. There they are, just a few of them marked. There are obviously other ones as well. Activate TRPM3 with a reasonably specific activator called pregnenolone sulfate. It doesn't matter much how we did it. And you can see that some of them are different neurons. For instance, that one and that one didn't respond to TRPV1, and some of them are the same. That one there and that one there obviously co-express TRPV1 and TRPV3 because they respond to both agonists. So we're not interested in those because what we want to do is to see the ones activated by warmth. And this is a warm stimulus, and you can see all of the neurons that expressed, like this one here, for instance, responded to both of those, and it certainly responds to warmth. But in addition, there are other neurons, if you have a look at this one here, didn't respond to any of those things and responds brilliantly to warmth. So some of those are shown here. So in amongst the population of known TRPV expressing neurons or TRPM expressing neurons, there are other ones which contain uncharacterized thermal sensors. So we found this interesting. And could we go ahead and clone them using some of the modern techniques that are available that were not available 20 years ago? So how do we do this? It's a bit of a needle in a haystack, I'm afraid, but we actually found a good strategy for going, if you like, from the animal to the molecule. And what we had was a big stroke of luck in that we found that sympathetic neurons, which are not thought to have a sensory function at all, these are pure motor neurons, but sympathetic neurons express this novel heat-sensitive channel in isolation. So here we've just bunged on the things all together, capsaicin and pregnenolone sulfate. We already knew that they didn't work, so we just did them all together. 2-APB, V4 agonist, etc. Nothing works. None of the TRP channel agonists had any effect whatsoever. But you put on a heat stimulus here, and you get this lovely big response. So this was really a stroke of luck, because we could patch clamp these sympathetic neurons. This was at rest here, and this was after applying heat, and you can see that the current activated by heat is roughly linear, maybe tails off down a bit down here, but really it's linear, and it passes exactly through zero. So anybody who knows about TRP channels is going to look at that and say, yeah, man, that's got to be a TRP channel. As soon as we saw that, yeah, that's right. But which one? Because there are all of these TRP channels in the mammalian genome. There are also a very large number of splice variants, so we have about 100 different channels to deal with. It's going to take an awful lot of time doing molecular biology, patch clamping, to get to the answer. So we had to do something a bit more clever than that. And what we did was look at the current voltage relationships, and you can see some of them, these green guys down here, for instance, are strongly outwardly rectifying, and it's clearly not one of those. Then there are ones that inwardly rectify. Clearly you could rule those out. But these black ones here, which are linear, there's still quite a wide choice of different channels available here. So we're getting a bit narrower, but how can we get in a little bit closer? Well, we had another stroke of luck because we were able to get a sympathetic cell line which behaved exactly like the sympathetic neurons. And with a cell line, we were able to extract messenger RNA and send it off for RNA sequencing. Something else we found about this cell line, and it was just simply a completely adventitious finding, I don't think it has any sort of fundamental importance, that we found if we put growth factors on the cell line, that the cold sensitivity was down-regulated. So with these pieces of information in our hands, we had enough to solve the problem. Because this TRPC1 channel that was expressed, these are the only channels that were expressed in the cell line that we had, but you can see that TRPC1 is upregulated by differentiation medium, while the cold response is downregulated. So it can't be that. So we had different arguments for all of them. We went through them, and it turned out that the only one that fitted was TRPM2. Now, TRPM2 is a channel that was already known to be heat sensitive, point 1, and it was already known to be expressed in DRG neurons, but nobody had thought of it as the warmth sensor up until we did this piece of work. So we were very fortunate to get TRPM2 knockout mice, which had been created by Yasuo Mori's group in Japan, and we extracted neurons from these mice. And you can see what we've done here is we're doing calcium imaging here, as I showed you in an earlier slide, and we're selecting only those neurons which don't respond to agonists for either TRPV1 or TRPM3. So these are novel heat-sensitive neurons. And as you put a temperature ramp on, you can see that you get a rather nice series of responses which are right here in the sort of warm range, sort of 35 to 40, so some of them are down as low as here. So this is a spectrum of all of the neurons in a big experiment of this sort. You get some that respond really down at quite low temperatures, and I think we still don't understand this. You get a group which respond out here at higher temperatures. But if you do the TRPM2 knockout, these animals are normal, viable, fertile, etc., but they have many, many fewer neurons. We don't still understand what these residual ones are, but the fact is there's a huge effect on the numbers of neurons. Well, you're not going to get that published in Nature unless you do an animal experiment, which we did. So these are our mice, and normal mice like to be at 33 degrees. 38 degrees is not painfully hot at all. I mean, you put your hand on it, it's only just slightly warm. But they don't like to make their home there. They'll walk perfectly happily across it, but if they're going to settle down for the night, they like to be at 33 degrees. So this is what you'll see. We're going to see 2 images of wild-type mice and 2 images of knockouts. These are the wild types, 33, 38, 33, and 38. So they're kind of exploring their environment. And then these guys, the wild types, settle down at 33. That's what they like. The knockouts, on the other hand, haven't really made up their minds. They maybe even prefer 38. So just to be sure, we swap the temperatures around, boom, like that. And you can see the wild types immediately settle down at the other end. These guys are very indecisive. They don't know where to go. Sometimes they're there, sometimes they're here. Just watch them. This is all speeded up, of course. The experiment lasted about an hour and a half. It's clearly they're not detecting the difference between 33 and 38, and in fact they end up at 38. So there's a clear behavioral difference in these knockout versus wild-type mice. I should mention that these mice were littermates. They were born to the same parents on the same day. They were exactly the same age. They were all males as well, no females, because the thermal behavior of females is a bit different. So this is the result of that experiment. There's the 38-degree temperature preference. Wild-type mice don't like 38. They stay away from it. There's the 50% level there, whereas the knockouts are really not statistically different from 50%. In other words, they're not detecting the difference between 33 and 38. But the other interesting thing is that the deficit of temperature sensitivity that these knockouts have is actually spread across quite a wide range. Even down at 23 degrees, you see there's a difference in the behavior of the 2 mice. So there's the normal behavior, sort of a normal distribution like that. They like best to be at 33 degrees. Sorry, the distribution looks a little bit like that. It's not very well drawn, perhaps. Whereas these guys are biased towards higher temperatures, as if they fail to detect the deterrent effect of mild, warm temperatures. Interestingly, when you get up to 43, which is an aversive temperature, both mice strongly stay away from that aversive temperature because, of course, this aversion for 43, which is a painfully hot temperature, is conferred by their TRPV1 and TRPM3 receptors, as was, of course, known already. As I mentioned at the start, the story is not complete. There seems to be another thermal receptor that we don't know about, but I think everybody agrees that TRPV1 and TRPM3 have an effect up there. So that's really the end of the story. I just want to point out some of the things we'd like to take forward with this. Firstly, how do we maintain body temperature? This seems to be a sort of $64,000 question that's completely unanswered. What's the molecular basis of sensation of body temperature? It appears not to be TRPM2 because we've looked at the body temperature of these mice and it's completely normal. So TRPM2 is expressed in autonomic neurons. Why? Does it regulate sweating and vasodilation? This is another area that we're looking on right now. It's actually almost anecdotal. They say women have a cold hand, warm heart. But women do have a higher body temperature. They have a lower peripheral temperature. So this anecdotal phrase actually has some basis in fact. So what we wonder is whether sex hormones might regulate TRPM2. And then, of course, another big problem is how do we sense extremes of cold? We are working on all of these things, but nothing at the moment to report. So I wanted just to finish with a picture of the McNaughton lab and to say that all of the work in this was done actually by a brilliant Taiwanese PhD student, then a postdoc, Chunxiang Tan, who for obvious reasons has permitted us to call him Jackson. And there is a picture of Jackson, and he did this huge study which involved a vast number of different techniques, all by himself. So thank you very much.
Thank you, Peter. Perfect timing.
Thank you.
So, questions.
Peter, I got one question for you. That you use that sympathetic neuron cell line to clone to indicate that trigger channel for differential trap. What seems to be different? The one before differentiation, the one after differentiation.
Correct.
How do you, and that kind of way you...
Correct. Very, very sharp eye, assuming that the referees in nature also raise the same objection. You're quite right. This doesn't go down very much, while the actual heat response is not completely abolished in the differentiation medium, but it does go down more than this. The question is whether this change is statistically significantly different from the change in thermal response. Now, the stats here are not great, and I think that the fact that this doesn't go down further is just probably variability. The stats are not great because we wanted to go for very deep sequencing of this, so to be absolutely, because ion channels are present at a very low copper number, of course, and we want to be absolutely sure we hadn't missed any ion channels. So these are the only ion channels expressed, we could say that conclusively. But the result is, it cost us £10,000 to get this information, that we couldn't repeat it too many more times. I bet if we'd done it more times, we would have found that goes down more.
And TRPC3 sometimes peak reduction.
Yeah, but we have good arguments why it's not TRPC3, which really, TRPC3 is one of these red ones, which is quite strongly rectifying. I mean, I have to say we use this information as a guide to tell us what we should do, but the subsequent information that we did here was, I think, absolutely conclusive, and also the behavioural things that I showed you.
I think there's heat sensitivity in the hypothalamus. Is TRPM2 involved in that as well?
TRPM2 is expressed in the hypothalamus.
Do you know if it has a similar role there?
It doesn't appear to, because we took our TRPM2 mice and put rectal thermometers in, and we had monitoring units in their necks, and we did them at play, we did them at rest, we did them when we cooled them down, we did them when we warmed them up, and we couldn't see any difference with the wild type. So that was our first thought, of course. Yes, it's going to be TRPM2, but it wasn't.
So a bit of comparative physiology in animals which have different body temperatures or don't regulate in the same way. Is there a different profile of expression of TRP channels?
I don't know. I mean, things like fish or lizards and things like that, I honestly don't know.
I mean, there are some weird, echidna and things like that have 30-degree body temperatures.
Yes. Yes. It sounds like a wonderful reason for a trip to Australia. Spend the English winter in Australia.
A question there.
Just going back to the RNA sequencing issue, I mean, you've got functional data, as you quite rightly said.
Yes.
Is there any reason to believe or know that TRPM2 is post-translationally modified?
I don't know. We do know which splice variant this is because it came out of the RNA-seq data. It's the canonical splice variant. Post-translational modification, that would be a possible explanation
Right.
for this sort of double humped.
Because you don't need gene expression. I mean, even if it's, we assume that 50-fold increase means something and small changes don't, but that's not necessarily true, especially if you've got functional data.
I think there are lots of puzzles here still, and this TRPM2 dependent response out here is rather puzzling, and what it is that brings some of them down into the warm range, I don't know.
And are there any antibodies against TRPM2?
And we were able to identify 5 available either on the market or through collaborators, and we tried them all, and they're all completely useless, I'm sorry to say. Well, we had the knockout, and
Yes,
we got
exactly.
stained in the knockout, so end of story. That would have been a hugely useful tool. We did actually localize TRPM2 to the DIG using in situ hybridization, which worked well.
And are these conditional knockouts or?
No, they're global knockouts. But they're bred from hens, which is the kind of right way to do it, which not everybody does.
Peter, phosphorylation sometimes play a significant role in the channel functioning.
Yes.
Is that an issue here? Just sweeping the answer.
I honestly, well, I would love to, since I've spent a lot of my scientific career working on that, but it's a possible explanation of this, but I honestly, I mean, life is short and I only have Jackson.
I must say that was a very warm presentation, so thank you.